But anyways, it's 12:10. Let's go ahead and get started with some stuff. Right before I dive into content for the day or anything else, I did want to open up discussion on the exam number 2, just one more time, and kind of moving forward to exam 3. So I know I've chatted about this with a couple different people already, but that was kind of on an individual basis. I'm going to be tightening my control a little bit more on exam 3 questions. If anybody has looked over the solutions at this point, they are available on Canvas by now. But the whole thing surrounding that and everything else, I still feel the equations and the number of solving things and everything else was, I think, around still where I would want it to be, right? There's not necessarily a ton of solving within all of those things. There's not a crazy number of calculations. However, the situations that you had presented to you were a bit difficult. You had to spend quite a bit of time looking at the situation, figuring out what's going on with these things, figuring out, what's going on in the problem before you can even write down an equation. And so I think that ended up eating a lot more time than I had planned for it to. So we're going to be looking a little bit more carefully towards exam 3, exactly what's going on with that, trying to make sure that's not as much of a factor. I do still want to have some of those questions, just perhaps not as many as we have had. Along with that as well, looking at the numbers, looking at the grades, the trend from exam 1 into exam 2, I am going to go against typical things that I would do, and I'm going to apply a very, very slight curve to the exam. I'm still nailing down exactly what that is going to look like. It is not going to be a major curve. We are not trying to match the average of exam 1 because exam 1's average was pretty high, all things considered. But just a little bit in there, something to put it a little bit more where probably more representative of how you would have done had the questions been worded a little bit differently. But I'll have that here sometime this week. I'm just working on figuring out what those numbers are exactly going to be, exactly what that's going to look like. Are there any other concerns, questions, comments on exam 2? Anything? We seem a bit quiet today. But if that's all we've got, I think we'll just leave it there for now then. Of course, as always, if you do have more things, you are more than welcome to reach out to me, however you choose to do so. Email, meetings, office hours, all sorts of stuff like that. Please don't hesitate to reach out to me, all that good stuff. I really do enjoy talking to you. Again, I have brought this up time and time again at this point, but I'm always happy to receive emails. In a worst case scenario, I can give you a hint and send you on your way. In a best case scenario, we end up having a little bit more discussion of what goes on with the problem. But I guess if we've got nothing else right now, let's go ahead and dive into the material. We are jumping into what is probably going to be our longest chapter here of the entire semester. That is chapter 12. So let me kind of give you a play-by-play of what we have done so far. When we started kinematics, we looked at kinematics along a line, and then we said, what about 2 lines? And then we said, what about in circles? And then we said, okay, enough of that stuff. We looked at dynamics. We said, what about dynamics along 1 line? What about dynamics along 2 lines? What about dynamics in a circle? And then we said, okay, forget circles again. Now, you can see where I'm going with this. We have looked at energy. We have looked at momentum. Both of those we have looked at along 1 line. We have looked at them along 2 lines. Now, chapter 12 is what happens when we look at those along circles. So, one of our very common problems here, as we are going to see these things. We will not forget it this time because we're spending so much of our time sitting here on circles. Now we are mastering circles. We are sticking on these for quite a while. We have looked at what we call translational motion. right? Translational motion is essentially, I am somewhere, I am now somewhere else, right? Of course, that's what you imagine when you're thinking about motion most of the time. I have to believe. However, you can have other types of motion. Translational is not the only type of motion that is out there. Right, I have brought up vibrations and everything else before. I have talked about oscillations before. None of these things I have talked about in any, like, real detail. I have simply talked about these things in terms of, like, when we're talking about heat and sound, vibrations and wave motions and stuff like that. But we haven't actually specified any of these things with equations. Vibrational we'll get to. Right, that'll be right before exam 3 in chapter 15. We'll start to talk about, or I guess not vibrational, but wave-like motion. Vibrational is going to be a little bit different. We're going to take a while before we actually talk about vibrational motion because it's really not anything that you talk about with a specific equation per se. You just kind of say, well, it's like microscopic, everything's buzzing around. Yeah, we'll put it in this corner and talk about it later. And then you never actually talk about it later, but that's fine because it's not a huge deal. But today, of course, I have already spoiled it. Today we are looking at rotational motion. And I really want to bring up that a lot of these things conceptually are not going to be wholly different from what you have already seen. When we're talking about kinetic energy, and when we're talking about potential, doesn't work quite the same way. But especially when we're talking about kinetic energy or work or mass or anything else like that, there are all essentially rotational counterparts, rotational parallels to all of these details that we have already seen so far. So as a quick review, here is a slide with a ton of information on it, but it is all supposed to be old information. When we're talking about rotational motion, whether we are in uniform or non-uniform circular motion, totally fine, either way. We generally like to specify two directions that are not x and y. We love to use the radial and the tangential components. Because generally speaking, as the thing moves around, the axes are constantly changing. But if you set it to be radial and tangential, then anytime if you've got a centripetal force or if you've got an acceleration, all of those good things work very, very, very well with those two new axes, rather than dealing with our classic x and y. But with all of those things, we have seen a few of these so far. We have talked about the centripetal motion, right? Essentially the force or the acceleration that you need to stay in the circle in the first place. You've also talked about a tangential acceleration, which comes from any time you're essentially speeding up or slowing down how you're moving around the circle. Now, we haven't talked about what causes a tangential acceleration, and that's coming up here. But you know conceptually, tangential acceleration, what it's doing. And then we've, of course, got all of our kinematic equations for rotational motion, right? And how there is a strong comparison for a lot of these things just along with what's going on with linear kinematics, right? All of those things, there's a simple translation over. Most of the time, it's just multiplying by r. That's how you get back and forth between translational and rotational. So all of that stuff, of course, we remember, right? Like it was yesterday. We've got all of this stuff down. Of course, look at this slide a few times, right? Reference this slide as we're going through some of these things. It'll help. So, we keep talking, I brought this up in the first point, but I haven't really talked about, what do I mean by a rigid body? Any object that is essentially not fluid, not changing shape or anything else like that. That is what I'm going to refer to as a rigid body. So for example, a calculator is a rigid body. That works out pretty well, right? A cup of coffee is not. A cup of coffee is not because of course that fluid is going to be doing things as it starts to move around. Right? It's not a stable object the entire time. Anything that's very bendy or anything else like that usually doesn't work super well either. Right? We're not talking about rope here. A rope is not a rigid body to rotate around because a rope is flimsy. Right? It only, and I struggle to say this in the first place, only if it's under very high tension where it's not changing shape at all. Then we might consider it to be a rigid body. But I'm going to say a rope, a string, chain, none of those things are rigid bodies. We're talking about solid objects. So, this could be done in a few different ways, right? At this point, it seems a little bit strange at first, but I really do want to highlight this point right here. It could be a group of particles fixed together or a continuous body, right? So a calculator is a perfect example of a continuous body, right? Like clearly it's got some shape, it's got some size to it. You can see all the different parts on this thing. Are you going to count the number of atoms that make up a calculator? No, you are not, right? I'm not going to do that. You're not going to do that. This number of atoms in this thing is way beyond countable for us. However, we might also be presented with circumstances where things work very well as particles. Right? Why do we keep occasionally some of these problems when I want to be purposefully kind of bland in a problem that will talk about a particle doing something? Even when we're talking about a block on a slope, our free body diagrams for all of those things assumes what we call it to be a point mass, a particle mass. Right? So what I'm getting at here is that sometimes we're going to have to think about real objects. Sometimes we're going to be able to take some of these real objects and we are going to approximate them instead as a particle. One that I've got in mind in particular is a dumbbell. Right? You know what I'm talking about? A standard free weight or anything else like that? A standard free weight is a perfect example. The handle, for the most part, very light, right? At least compared to the weights on the side. Not doing a lot in the handle. The weights on the side are, in like the cartoon sense, circular, or in such a uniform shape that we can more or less treat them as particles. Then if we're talking about spinning a dumbbell in some way, we have one particle fixed to another particle by some handle that is, for the most part, not a big deal in the rest of the shape. That's a perfect example of a group of particles fixed together, right? Some combination, different pieces like that. So, for the most part, right, and I know this is in the reading and everything else presented in this way, that if something is just floating in space and we slap it, right, and we don't slap it dead center, we slap it on one side or something else like that, it's going to start spinning around, right? Maybe our slap also gives it some translational motion, but for the most part, we're talking about something just spinning. That object, as it is spinning, is going to be spinning around the center of mass, a pivot point. Right? Most of the time we're going to be talking about these things in terms of rotating around the pivot point being the center of mass. Sometimes we can have it be a slightly different thing. But it's going to rotate around some point, and then all of the different particles making up that rigid body are going to be spinning around in a circle, right? Spinning around that central point. So, for all of these things, one of the things that I do need to specify, these are equations that you have seen so far already. Angular position, angular velocity, angular acceleration. Sign convention is that counterclockwise is positive. Just as you have seen with your classic unit circle, right? When we start from positive x0 and then go counterclockwise around, same deal. Counterclockwise is what we call the positive direction. The other direction is negative. Clockwise, right? Anti-counterclockwise if you want to get extremely complicated. But all of our, I've brought this up, all of our kinematic equations are exactly the same in rotational. Now we're just using the rotational counterparts, right? No real difference there. Everything else kind of lands up to be just the exact same. So I want to try this in a problem real fast. Let's imagine an ice skater holds their arms outstretched as they spin at 180 rotations per minute. What is the speed of their hands if they are 140 centimeters apart? Take 2 minutes. Come up with a number here. So let's start taking a look here. As we would have this thing, I'm going to try and draw it out like this. Let's draw a person very badly. Let's imagine, let's do a top-down view. Oh, draw pad, please. Or is it PowerPoint? Who knows? Top-down view. This is roughly what I imagine a person looks like. There's the head, there's the hands. Right? We all agree? Well, like a head of dark hair. Perfect. So, what we are given is some sort of rotation per minute, some measure of our angular speed. It doesn't really matter which direction we're going with this one, because we're only interested in speeds the entire time, but I'll go ahead and write it out like this. Let's draw our little omega. So we're spinning around this entire time. Now, we know that their hands are 140 centimeters apart. So our radius is not 140 centimeters. We are rotating about the middle right here, right? This, I will increase the circle. We are orbiting around this central portion right here. So our radius is actually only going to be 70 centimeters, which I will immediately rewrite anyways as 0.7 meters, right? I love those standard units. So I've done that. That's one piece here. But realistically, we're looking for the speed of their hands if they are 140 centimeters apart, the speed as compared to the angular speed. Remember here, we're looking at V, speed, is equal to omega times r. So then we have the speed if only we have omega, and we technically have omega, we just have it in a dumb unit. 180 RPM is not a very useful thing for me, so this is rotations per minute. What I would say here is I want to cancel out those two things. I would say in 1 minute, there is 60 seconds. In one rotation, there is 2 pi radians. Breaking up those units just like that right there, we should end up with something on the order of 18.85 radians per second. Now I am in a standard unit, 18.85 times my 0.7 meters should land me with a final speed of 13.19 meters per second. How do we feel? Are the terms coming back to us? Do we kind of remember these equations? I know it's been a little while since we've really needed to use these. Okay, so that is our V is equal to R, or omega times R equation, but I want to try one that's a little bit more complicated here. Let's imagine a high-speed drill starts from rest and steadily increases its speed until it reaches 2,000 RPM. So again, RPM, not a very useful unit for us. We want to convert that. It does that in a time of only half a second. So, what is the drill's acceleration? Not angular acceleration, but acceleration. And then, and when we're talking about the acceleration, we're talking about the outside edge. How many revolutions does the drill make in this time? Take the next 3 or 4 minutes on this one. You might want to, again, use this slide for reference here. You can find that on Canvas if you're not looking at that thing already. It might help to have that up on the side so you can look at those equations as you need them. So go ahead and spend the next 4 or so minutes on this one, though, and then we'll talk about it together. All right, let's start taking a look. And the first thing I want to do here, if maybe you're still a little bit fuzzy with some of this rotational motion stuff, I want to try and retranslate this into something here. Let's imagine, let's kind of draw it out like this. Starting from rest, you can accelerate. So let's say V0 is equal to 0. And let me do this in a slightly different color. This is not exactly the problem that we're looking at. This is kind of a recontextualizing some of these variables, some of these concepts. You know that you start from rest. You know that you accelerate to a speed, let's say 2 meters per second. And you can do this in a time, delta t, of only half a second. Right? This is like a push off with your back foot and you're speed walking. Here's what you got. We're asked to find the acceleration and the distance traveled, more or less. Let's imagine at the same time that you're doing this in a... my 2 questions could be reframed as essentially for A, it is what is the acceleration? And of course, if we were to find that, it would just be, I would say, okay, we'll take my difference, delta V, which is really just V final here, divided by delta T. I could recontextualize B as how many times do I go around a 1 meter loop? Let's imagine I've got like a really small little loop. I'm walking around in circles for some reason, which is not an uncommon thing. But let's imagine that I'm just walking around in 1 meter circles. Then essentially I'm asking how many times do I go around the loop? That's an easy enough thing to find. I would just say, okay, well, I've got an acceleration, I've got a time, I've got a distance that I need to cover. How many times do I cover that distance? Right? It's find the distance, divide by however long the loop is. All of this is essentially the linear translation. If we had done this in linear motion rather than rotational motion, we already know what to do. This is old kinematic stuff at this point. And rotational motion, though, I'm trying to convince you here that what we're looking at is no different. We start with an angular speed of 0. We end with an angular speed of 2000 RPM. Now, immediately I say, RPM. Yikes. Right? Somebody didn't get the memo. We don't like that unit. We like to have standard units. And converting that into standard units, you should find something like 209.4 radians per second. So now that's in standard units. I'm happy with that. Our delta t, time can't be rotational, unfortunately. So it's still just 0.5 seconds. But if I'm looking for a tangential acceleration then, right, there's a few ways that I could consider doing this thing. I could say, all right, I put my foot in my mouth earlier, didn't I? Drill's acceleration doesn't really make sense without the size of the drill, does it? I thought about this the wrong way and led you down an incorrect path. I apologize for that. What I should be saying here is not drill's acceleration, drill's angular acceleration. Let's solve out for that. Because we don't know anything about the drill. We just know how it spins. Could be any drill bit. So I'm just going to say angular acceleration. Let's look for that. In that case, alpha would be delta omega divided by delta t, which we know here, omega final minus 0 divided by the same 1/2 should get us some sort of quantity like 418.9. Now this is a little bit strange, but think about it for a second. Radians per second squared versus meters per second squared, right? The distance that we travel for rotational is just radians instead of meters. Now, if we needed to find some sort of regular translational acceleration, we could just at any time multiply alpha by the radius as we would see it. But we don't know anything about the radius, so I apologize for that one. We don't have anything in the radius to actually solve for. So let's ignore that for a minute here. So we've got that. Now we need to find, and probably the more important one here, how many revolutions do we actually make in this time frame? So there's a few different ways that I could consider this one. There is a way to do this where you're looking at rotations the entire time. You never move into radians, but it's a little bit weird. I prefer to just work in standard units and then we'll change to things as we need to. That's a little bit easier for me. Then there's one central path. So in doing this, what I can imagine is we're talking about revolutions. We're talking about distance covered, in a sense, right? Rotational distance covered. So if I want to know where I end up, and I know I started from, call it 0. Let's just call that 0. And I know that I started with no speed, then the only part that's actually going to matter here is my 1/2 alpha t squared, right? And this is just, again, our kinematics equation. If we're looking at it like that, x of f is equal to x initial plus v initial times t plus 1/2 at squared. No different. The equation that we use is more or less the exact same. It's just rotational rather than linear. Right? The variables are different, but the equation is the same. So in doing that, what we find is that our total distance covered in radians is 52.36 radians. But that's not my answer. What do I have to do with this? This is not a revolution. A radian is some amount around a circle, but it's not the full way around a circle. How many radians are in a circle? Two pi, that's exactly it. To go all the way around a circle, it is 2 pi. So it's right around 6.28 radians per circle. So what I'm going to do is I'm going to take this quantity right here. I'm going to say, okay, well, in one revolution, one full way around all the way around the circle, there are 2 pi radians. We do that over here, and what we end up with is 8.33 revolutions. How are we feeling? Excellent. Hopefully it at least feels kind of familiar, right? It's stuff that we have talked about a little bit before, maybe not the tangential acceleration as much. We talked about it conceptually. We're like, this can be there, but we don't want to worry about it too much quite yet. Right, but we've seen it actually in a lot of different problems. Anytime we're looking at like going around a roller coaster loop or anything else like that, technically speaking, those are all situations where we do have some tangential acceleration. We just haven't cared what the tangential acceleration was. It hasn't been a factor for us yet. Now we're going to start looking at a little bit more details to what it actually is. Speaking of all of this good stuff that we've got, right, I brought this up earlier about when we have some sort of collection of masses or anything of the sort like that rotating around most of the time. So when we say an unconstrained rigid body, what we mean there is that nobody has stuck a stake through it. Nobody has any crazy other forces acting on it or anything else like that. This thing is free floating in space, right? It has gotten away from the space station. We're never getting this thing back. If it is going to spin, it's going to spin around what we call the center of mass. And I'm sure this is a term that you have heard at some point or another, right? Of course, there were tons of Flash games, the whole thing about, lowering your center of mass, things like that. All of these details around something. What is it? Well, generally speaking, it's an average. If you take every mass and where it is at, and you essentially plot all those out and say, okay, well, the mass is here, and this is how much it is, and we sum all of those things up together, we get a coordinate, an XY coordinate, or XYZ coordinate, if you want to get crazy with 3 dimensions, of here is exactly where we say the center of mass is. This is on average, if we were to pretend as if this thing were just one single particle, on average, this is right where we would put that. What has the lower center of mass? A car or a van? Car. And if you've taken a driving test, that was probably one of the questions on that driving test, right? The whole thing about warnings for like semi-trucks tipping on certain banked roads and everything else like that, depending on what the curve looks like or anything like that. All of those are situations where there is a difference in where the center of mass is. So if a semi is on a curve versus a very low riding car, the car has a much lower center of mass. It is probably not going to tip over, right? It's going to be real hard for that car to tip over. But the semi, its center of mass is somewhere in the middle of the cargo of that thing. And that's much more likely if it's going to tilt about that center of mass. So that's why this is of interest to us. And how we actually calculate this thing out, I know this looks a little bit scary at first, but really all this is doing is this is saying, take the average, a weighted average, and quite literally weighted average. Please don't test flipping the semi. But I'm going to say, take the total mass, right? It's kind of like an average in that sense. We're going to divide by the total mass at the end of the day. But what this is really saying is take mass 1 at x1. Add to it mass 2 x2, add to it, so on and so forth, for as many as we've got, right? That's all that this is saying right here. This is just a summation if you haven't seen this in a little while. So we do that for x, we do that for y. We can treat them separately, as we can do with a lot of different things in physics. And then, of course, capital M is just our total mass. Sum up everything you guys got together, one big measure in kilograms, divide your sum by that quantity. So I want to try it. Right here, this point, that's what I'm calling 0, 0. So what I want you to do is find the center of mass relative to this 0, 0. Where is the center of mass on this picture given this scale? I'm going to say take the next 3 or 4 minutes to come up with an answer for this one. And then let's see what we've got. We'll talk about it together. I would probably argue that for the axes, we should have those set in standard units. But this will be kind of a low pressure place to do that anyways. Let's go ahead and start taking a look here. And I'm going to run into a disaster like I always do about where things are. And let's pull up the snipping tool and see what we can get out of this thing. Get a mostly all right picture, copy this thing. This has been working significantly better for the most part than actually just copying and pasting otherwise. So we need to find the center mass of this thing right here. Right. So let's use those brand new equations, right? What else do we have? What I can start with is my x equation. I'm going to say, all right, well, the x center of mass is going to be when I take, essentially, I'm going to divide by the total mass. And inside of these parentheses right here, I'm going to take every single mass and where it's at in the x-coordinate and plug that in. Now, before I do this, let's think about it like this. Well, let me go ahead and do this symbolically to start, and we'll talk about it then. Well, sorry, I'm going back and forth here. What's the easiest way to talk about it? Let's go ahead and just, I'll use MB, but then let's actually use the x location. So, if we start mass of A times x is equal to 0, right? That's where it starts. Mass of B, x equal to 0. Mass of C, x is equal to, I will go ahead and use standard units here, so 0.1. Mass of D, same deal. It is over 0.1. It doesn't really matter where this thing is at in y. That's not something that I'm worried about. Now, my question is, do I need to worry about converting my masses to standard units, or can I just leave them as is? What do we think? Does it actually matter if I, yeah, why? So this is kind of a trick question to pull you into it. Why is it safe to leave them as is? Why do I not need to bother converting those? Yeah, masses are, I'm essentially dividing by the masses, right? All of these spots right here, whatever unit of mass I plug in at this one, whether it be kilograms or grams or, I don't know, perhaps number of marbles. Let's say I've got a really nice marble that I like to scale everything to. How many marbles worth is it? Any unit that I would use would be totally fine as long as M of A, M of B matches the total mass at the end of the day here. And yes, it is indeed. 0.1 is the distance, not the mass. So what I'm going to do right here is I'm going to say 200, 200, 200, and 100. That is a total. Capital M is equal to 700 grams. I'll just leave it as grams. That's totally fine. I'm going to take all these quantities. This one doesn't matter. This one doesn't matter. I'm going to take these other two quantities. So I've got 200 at 0.1 and 200 at 0.1, all of that good stuff summed up together, divided by 700 kilograms, is going to land me in a pretty nasty unit, if I'm being completely honest. Right, anything divided by 7 is not kind. But what we get at the end of the day when we plug all these quantities in should be something like 0.05714 meters. right? Because that's what I plugged in right here, meters. If we had left this as centimeters, I'm not that upset by that, right? That would be totally fine, because this is equivalent to 5.7 centimeters. Totally fine. So that says right off the bat that our x-axis, or at least the center of mass in x, is going to be somewhere a little bit more than half of the way over. Perhaps something like this. Right? Just barely over half, not by much. Now, let's go ahead and look at the y direction. Y, center of mass, will be equal to, again, 1 over m. I'm going to take these things piece by piece. So I'm going to say m of a, where is that on the y-axis? It's at 0. mb, where is that? That is at 0.08. mc, also at 0.08. md, at 0. That's gone. That's gone. MB, MC, those are my two driving factors here. I've got my same 700 grams from before. What I find for my y-axis is that my center of mass is at 0.04517. Oh, 571. Whoops. It's always a strange repeating pattern when you divide by sevens. Meters, or, again, 4.57 centimeters. So that's a little over halfway again. Versus our 8 centimeters, we would expect our center of mass to be right around at this point right here. And that makes sense, because we're almost in a symmetrical shape. We're almost dead center, but this one right here doesn't have as much mass. So my center of mass is going to shift away from that lighter corner and be a little bit more towards the heavier side. There are some numbers that could be worse. We do not hate 7 nearly as much as we hate friction and drag. And even then, I would not put friction and drag on the same category either. Drag is a different beast. But how are we feeling on this one? M is all of the masses together. Yes. All right. So let's look at the scenario. So this is fine when we have a bunch of point masses, right? And there's already, I imagine, a little bit of groaning here as I bring this up. Point masses, summation, totally fine, right? No big deal with that. What happens when there's a lot? What happens when we have so many that counting them by hand is no longer a very practical scenario, right? Of course, it's our very good friend, calculus. Along with its buddy integrals. This is not the worst thing in the world, realistically, if we're being completely honest here. This could be a lot worse of an integral. But generally speaking, what we're trying to do here is we're trying to say how much mass, what is the density at that spot versus where it's at right now. That's all that we're really doing here. We need to know some expression for d of m, because this is a little bit strange and we haven't talked about this in a heavy detail quite yet, but you need some way to talk about what's going on with d of m. That is, how much mass do I have in this infinitesimally small point? I don't necessarily know how to integrate that on its own. If it was dx or dy, totally fine, right? I know how to do those. We've done those. Those are lines. Those are directions. But d of m is like, how do I make sure that I have summed up everything that I've got. What are my bounds for d of m? Is it like 0 to the 100,000th piece? I don't know. What we need to do for a lot of these things, this looks a little bit simpler than it is in practice. What we need is some expression. Need, and I know you probably can't read that, need an expression. That's what I'm trying to say, though, for d of m. Right? We need to know, how does d of m translate to things like x and y? If it's a constant value, perfect. You're golden, right? Then it's just essentially a density, and you multiply by the space that you've got, all that good stuff. But if it's not, if it's a little bit more complicated than that, you need an expression for that to actually do this integral. Keep that in mind. But for the most part, we're going to be using a bunch of known integrals, and I will walk you through some of these things that we're going to calculate, and we're not going to go through necessarily crazy ones. So now for a complete left turn off of what we were talking about. Something called the vector cross product. Right, so this is completely separate from what we were just talking about from center of mass, but it is still a very important thing because we're using all of these things together, right? Today is the day that we are using to essentially build up our tools for the rest of chapter 12. Understanding center of mass and how something's going to rotate, fantastic. We need that, right? Of course, if all of this is about how do things rotate around, we need to know what's it rotating around. Cross product is going to be a very important thing because it's going to have a lot of different quantities being calculated using a cross product. So I think I brought this up when we talked about dot product, but the thing that I mentioned was that the dot product is one way to multiply vectors together. One way, not the only way, but one way that we could do it. The cross product is another way. And this is also why I didn't just say that, you know, it's the only way or anything else. There's a little bit of, a little bit of foreshadowing going on with all of that. But here's what it is. Two different ways to consider this thing. One of them is going to be a little bit easier to do at first. And we're going to start with that one, right? Just like the dot product has, the cross product has a very easy way to talk about it. If I have two vectors, A and B, and if I want to find the cross product, then I'm going to say AB sine of theta, that's my magnitude. Cross product is unique from the dot product because a cross product produces another vector. Right? Remember that the dot product takes two vectors, shoves them together, makes it a number. The cross product is going to take these two vectors and come out with a brand new vector from them. What is this right-hand rule nonsense? Well, in a sense, when we're finding the cross product, what it's doing is how perpendicular is A to B, and then the direction of the cross product is perpendicular to those two. If you have understood any of that so far, this might help. We need X, Y, and Z, right? We have jumped into the third dimension at this point. This is hopefully nothing super crazy or anything else like that, but here we are. There are three different ways to think about the right-hand rule, and the first step, if you are using the right-hand rule, is to use your right hand. Jokes aside, I have seen many, many, many times somebody has a pen or pencil in the right hand. They're writing away. They're doing their exam. They're doing whatever they're doing. They do the right-hand rule. Here's the issue. This doesn't work. This gives you the wrong quantity. Don't do that. If you're about to do the right-hand rule, consciously set down whatever writing utensil you've got. Sit on your left hand if you want to. Use your right hand. But here are three different ways to consider this. And this is all about finding what direction my cross product is going to go, right? So this doesn't tell you anything about what's going on with the quantity or anything else, but it is telling you about the direction. One of the ways to consider it is take your right hand and do this with me right now, right? And I've got this specified. You can see my three fingers that matter here. I'm going to say, okay, take the direction of A. Take the direction of B. Your middle finger, or the other fingers along with it as well, if you want, point in the direction of the cross product. That's one way. The other way to do this is that we start from A and we curl our hand towards B, and then the cross product is the direction of our thumb. And I'm going to assume that your fingers turn one way, right? If you can bend your fingers all the way back, I'm sorry, I've got nothing for you, right? That's maybe method one works a little bit better for you. But my fingers only turn one direction, at least controllably, right? Somebody could maybe send them the other way. But if I curl my fingers that way, then my thumb points in the direction of the cross product. The last way, if you're not so good with your hands or anything else like that, but you have used plenty of screwdrivers and you've screwed plenty of things in, then the other way to consider this is that our classic righty-tighty, right? If we turn it to the right and it goes downwards, that is similar kind of the rotation, the direction. Our right hand rule matches up with that pretty well. I've got story time with this. You ready for this one? And I'm positive that they don't follow me or anything else, so I can freely give away this story. I was in a 400 level physics course, one of the harder ones. I was sitting next to somebody, and this is when I was drinking like 2 pots of coffee a day. It's a 10 o'clock class. I've drinking a lot of coffee in my life. But, so I'm 15 minutes into the course. We have to do a cross product, right? Cross products show up in a lot of different places. We do a cross product, we get a quantity out. The person sitting next to me says, I think that should be negative. I see the writing on the wall because this is not my first rodeo. I decide, you know what? Now's a great time to take a break, right? It was my second class of the day already, so I decided I'm going to go down into the basement, start a brand new pot of coffee. I figure that I'm going to have a little while before I need to actually get back into the classroom. So I sit there and I wait for it, and I don't have it with me right now, I have a giant mug that holds 6 cups of coffee. So I poured my giant mug of 6 cups of coffee, and I decided to go upstairs and see who was in the lounge. My best friend was in there, so we chatted for a little bit, we made some jokes, I got through my 6 cups of coffee, and I decided I'll get a refill and then I'll go back. I go downstairs, I get my refill, I get caught up in the lounge again, chatting with somebody else. I realize, hey, I've been out of the classroom now for about 45 minutes. I walk back into the classroom. We're still arguing. We're still arguing about that negative sign. They're convinced, they're doing the math, they're doing everything right, it should be a negative sign. For whatever reason, we can't get the class back on track. I sit down, 5 minutes, I'm kind of zoned out at this point, if I'm being completely honest. And suddenly they go, oh, whoops, I was using my left hand. Don't be that person. Use your right hand. Please. for all of our sake. Please. And I bring that up because anyone can get caught in this thing. Right? That is a very important detail. Anyone can get caught in this. I have seen all sorts of people get caught on this one. Find one of these rules that works for you. Whether it be the first, the second, or the third method. Whichever method works best for you, use that. Use that to help inform your direction as you are going through these things. Right? If we want to talk about this thing in a little bit more detail, if you're not entirely sure which one to go with, both the first and the second have some similarities, realistically. But if we're looking at this thing, I would recommend the second method is usually a pretty decent one here. Right? I like that one pretty well. You've got to do some weird things with your arm like this sometimes to make it go in the right direction. Like for this one right here, if I'm imagining this thing, I need to say, okay, A needs to point this way, and then I need to curl towards B. So I need to tilt my hand and do this to curl that way. And that's how I know that if we're doing this thing, what direction does the cross product of A cross B go? Into or out of the page? What do we think? Into the page. That is exactly what I'm thinking as well. And I have no idea where to get a 6-cup mug. I have 4 of them at this point. They're amazing. I use them for everything. But something like that. I think the second one is a fantastic one. right? The second method is a really good one to use, but I use both 1 and 2. Both of them are pretty nice to have. How do we do this example? Start with your fingers, the 4 of these things, pointing in the direction of A. So if I'm looking at this thing right now, I could do it like this, I could do it like this. One of the two, right? And then I need to say, okay, I need to curl my fingers towards B. I need to twist my arm like this to make this happen and then curl it towards B, which I know is backwards on your screen, but it's what it works for me. So you got to essentially twist your arm around like that. You look like an idiot, but you know what? We all do. That's fine, right? Curl your fingers from A to B. The direction of the cross product goes into the page. Very useful to have. But this brings up a very important point, because if we were to go from B to A, that's, for one, a lot easier physically to do, but it leads to a little bit of a problem. B to A gives you a different direction. So whereas the dot product, it didn't matter. A dot B is the same as B dot A. Totally fine. But when I'm looking at cross product, it doesn't work that same way. What we would say is that it doesn't commute. A cross B is exactly the negative of B cross A. So keep that in mind. As we're looking at these things, you need to be careful with them. Right? You need to pay attention to this direction. It goes from one to the other, and you have to be tracking which one goes to which. So, I want to start with this, though. We've got 2 different sets of vectors here. I want you to take the cross product of each of these, give me a magnitude and a direction. Take the next 2 or 3 minutes, and let's come up with some answers here. What sort of nonsense am I coming back to here? For anyone wondering as well, this is the mug. I love this thing. This has gotten me through all of undergrad and grad school altogether. I got it in a care package when I was a wee freshman. It was a part of a care package. But let's go ahead and look at some of these things real fast. So we say, all right, this is supposed to be, essentially speaking, AB sine of theta for the magnitude, right? That's one part of this. So if we're doing just the magnitude, then we're in a pretty all right spot. A cross B, so that's going to be A 6 times 5 times sine of 45. If you had forgotten and accidentally done a dot product, you would have come up with the exact same answer. A cross B should give you 21.21. But now what direction does it go? What do we think? Into the page, exactly. I need to contort my body again, right? I need to do something like this so that my hand can go from A to B. Then my thumb goes in. The other way that I can consider doing this is to follow the first rule. I could make A and B point in similar directions. And if I do that, I would do A, B. The result, again, goes into the page, right? And this is the nice part about the rule 1. It doesn't have to be like an exact 90-degree angle. I can say, hey, this can be, whatever. If it's 45, it's 30, whatever it is. The general shape of where these things are pointing is going to give you the direction that this goes. So this is 21.21 in, or I'll say into the page. If you're wondering how we draw this out, how do we actually specify whether something is into or out of the page? I've got a fun little symbol here. Into the page will look like this. Let me do the other one first, because it's going to go hint out of the page. But this one, 4 times 6 sine of 90, means that this result is just 24. And of course, coming out of the page this time. And that symbol is something like this. What this is an arrow. If I draw an arrow, kind of like this, you're either seeing the tail feathers as it goes away from you, or you're seeing the head of the arrow coming directly at you. That's the symbols that we use, or those are the symbols that we use for into and out of the page. If you're looking for direction, right? So we might see something we can imagine here. I want to make sure that I get these directions correct. I could say something along the lines of X, Y, and Z. Like that. That's how I might specify my 3 axes. As needed. So, I want to try one more of these. How do I do this cross product? Does anybody know? Does anybody have a good answer? How do I find the angle between these two? There's a little bit of screaming involved, I think, right? Usually, that's my method here. I do A. A's not bad, all things considered. A, I'm like, all right, so it's got an X component, it's got a Y component. I can do that. That could be worse. But then I look at this thing that's got an X, a Y, and a Z component, and I say, all right, never mind, right? We're done. We had a good time while it lasted, and now we're going on to something else. But fear not, just like in the dot product, there is a different way to do this, using the common vector notation rather than dealing with just the magnitudes. And that method, well, we need to remember everything about matrices. Not everything about matrices, but a few things about matrices. If you need to find the cross product, and let me go ahead and do this one. We're going to view this thing in slideshow because I think that's the easier way to look at this. If you have vector components, here's what you need to do. You need to take a determinant of this thing. Imagine here, let's start with the 2 by 2. A, B, C, D, they're just numbers, whatever numbers they are, 2, 3, 4, 5 if you want. Lay them out like this. When I'm taking the determinant of a matrix, I've got flat lines on the sides rather than the big brackets. So I'm going to take A times D, I'm going to go over, and I'm going to take C times B. Anything going down diagonally is a plus. Anything going up diagonally is a minus. So that is AD minus CB. If we do this more, if this gets larger, like for example, a 3 by 3 matrix, then the proper way to do this, for being proper, is to first, I'm going to say, all right, start with A, cross out everything else that's on the same row and column as A. Right, so if I'm looking at A, I'm going to take A, and then I'm going to get rid of everything else on that side. And what I'm left with is A and a 2 by 2 EFHI. So I'm going to take A times the determinant of this 2 by 2. Then I'm going to take B, and I'm going to do the same thing. Cross out everything in the row, cross out everything in the column. Now I'm left with B times a 2 by 2. Alternating signs, so that's a minus B times this determinant. Finally, C. Cross out everything in the row and column, take what's left, 2 by 2 times C. To get this lovely equation. Right? It just works. Very easy to do. Of course, I'm sure you guys already have this one memorized. I am, of course, being sarcastic. This is a long and pretty tedious process. The reason that we like this method, it's not the method that we use, but it's the method that we like. And the reason that we like this method is because this scales up. If we needed to do a 4 by 4, this method works just as well. If we needed to do a 7 by 7, this method would work just as well. And there are actually a lot of different reasons that you need to use determinants. If you have taken linear algebra, and I do recommend that you do because it's a very cool course and it's a very useful course, but if you have taken linear algebra, then you'll have seen some of the different things that you can do with it, but my biggest problem with that course is that I don't think it's contextualized very well. A lot of things like eigenvalues and eigenvectors, you're like, what good are they? But there's a lot of good to be had from them. They've got a lot of very strange uses, places that you don't expect them to show up, but they do anyways. But all of that said, there is an easier way. at least I think what everyone else believes to be an easier way. So if we were to do these things with vectors, first, let's go ahead and follow that exact same method that we just saw from before. Take my two vectors. My 3x3 determinant is essentially going to be the 3 unit vectors, A, B, row by row here. So that is to say, I'm going to take I hat of that piece minus J hat of that piece plus K hat of that piece. And we get this nasty looking thing. So one of the ways that I like to think about this is that I'm kind of like in a rotating door with X, Y, and Z. We see the X component depends on AZ, or the YZ minus YZ. A comes first, so A gets in there first. The J component goes X then Z minus X then Z. And then I like to think of this, it goes Y and then Z and then X, because A is supposed to come first. And then Z depends on only X and Y. No angle, no right-hand rule, just the final vector form when you're finished. Nice for that reason. Now, I keep talking about this slightly nicer method to use. Discard those annotations. Here's what we've got. This is a rule called Cramer's rule, and I'm positive I'm not going to do this particularly well. And when I say not particularly well, I feel confident that I can do this rule. I feel confident that I can show you this rule. I'm sure somebody out there online has some really wonderful animated graphic to show this thing better than what I'm about to do right here. But let's try this. Right? We're not in that random YouTuber's classroom. We're in my classroom. So I'm going to write this thing out kind of like this, kind of like this. And let's imagine we're doing A cross B. What I'm going to do is I'm going to start with the exact same setup. I hat, J hat, K hat. My A vector. My B vector. Then I'm going to take the first 2 rows and I'm going to repeat them. Or not the first 2 rows, the first 2 columns, and then repeat them. Now what I'm going to do, first I'm going to create a new layer so that we can actually draw on top of this thing, and that's not a big deal. I'm going to take, kind of like I had with my 2x2, I'm going to take a diagonal line down. And then I'm going to take another one. And then I'm going to take another one. These 3 diagonal lines, I'm going to say I hat, A of Y, B of Z, plus J hat, A of Z, B of X, plus K hat, A of X, B of Y. Then, just like the 2x2 again, I'm going to take all of the up diagonals. 1 up diagonal, 2 up diagonal, 3 up diagonal. So I have essentially accounted for every single value. I know A of X looks lonely right here, but it's getting covered twofold over on the other side here. So every value has been accounted for, and every single value essentially has 2 colors overlapping it. Or every single quantity, every single number has 2 different colors overlapping it. I'm going to subtract all of my red pieces. So this is now going to be, I'm going to start with my K hat, but I'm going to do the BXAY. I just like to have my K hat out front so that I know which direction it points in. Minus my I hat, BYAZ. Minus my J hat, BZAX. And when we slap all of this stuff together right here, this turns out to be exactly the same thing as we had found right here. No different. This has grouped it nicely for us, but we had to go through this to get to that nice grouping. And I'm not a fan of that, if I'm being completely honest. It feels a little bit extra, right? Somebody can do that and everything else, but I would look at them and I would be like, why? Why do you do this? Don't be like that. Just use Kramer's rule. Kramer's rule is a little bit easier to run through. So, and it's spelled with a C, I think. I'm fairly certain on that one. I know I misspelled it for years, and I'm pretty sure I misspelled it as a K. But Kramer's rule for determinants makes this whole thing a lot easier to parse through. I highly recommend it. So, let's practice. I want you to find not only the magnitude, right? Realistically, to find the magnitude, what you first need to find is the cross product of A and B. Find the cross product of A and B, find that vector, and then find the magnitude, and that'll be our last question for the day. So I'm going to say take the next, say, 4 or so minutes to work on this one. And then we'll take a look together. Speaking of, though, let's go ahead and start taking a look at this thing. So I'm kind of in a strange situation. Again, these are the same variables that we just saw last time of like, what do I do with this? Right, this thing's a mess. I can maybe feasibly draw A, but drawing B sounds like a nightmare because I would have to find a good way to draw all 3 axes so that they look at least kind of all right. And then I would have to figure out some way to essentially scale. I've got an X, Y, and a Z component, and scaling that properly on my picture is probably best left to the textbooks. I'm not going to think about the direction too much in that sense because kind of just in the same way, when we're thinking about magnitude and direction, that's one way to think about it. But when we did vector notation kind of takes care of that for us. It tells us how much is in X, how much is in Y, how much is in Z. We've sacrificed knowing the full length of the vector for a little bit more specific information about each direction that it's going in. So let's take our variables as we've got them, or take our vectors as we've got them. I'm going to do something similar to what I just saw right here, and I'm not just going to steal the result because I want to practice this. This is 3i hat plus j hat, and my b vector is going to be 3i hat minus 2j hat plus 2k hat. So let's go ahead and set this thing up just in the same way as before. We're going to take this determinant, and I'm going to draw this thing nice and big so we've got plenty of space to see what's going on. I'm going to take my I hat, j hat, k hat. Okay, let me actually fill in the real things here. So we're going to say 3, 1, 0. And again, repeating those first 2 columns, 3 and 1. Then I'm going to take 3, negative 2, positive 2. Repeat the first 2 columns. Now, let's go ahead and actually do this properly. Okay. So with that, my positives are going to be essentially, I've got I hat times 1 times 2 plus j hat times 0 times 3 plus k hat times 3 times negative 2. Take all my reds, so I'm subtracting from that. Start with my first diagonal, up k hat times 3 times 1 minus I hat times negative 2 times 0 minus j hat 2 times 3. So cross out the things that don't matter. 0, 0, we don't care about those. What I am left with when I take all of these things summed up together, I'm going to have essentially my 2i hat. I see only one thing has anything to do with j hat, so that's a minus 6 j hat. And then I've got a minus 6 and a minus 3 in the k hat direction, so that's a minus 9 k hat. There is my resulting vector. How do I find the magnitude if I've got 3 different pieces? Does Pythagorean's theorem scale up? Of course it does. And it works out just fine. We do exactly the same thing as we would normally do. So the total magnitude, I'll just do magnitude, is equal to the square root of 2 squared plus negative 6 squared plus negative 9 squared. Pythagorean's theorem is wonderful for that reason. It works for as many components as you could possibly want to have. At the end of the day, it comes out to be a nice, clean 11. And there we are. I know Kramer's rule is a little bit long, but I think it's a much simpler way to go about things. I think it's a lot easier to write out, a lot quicker to do, than trying to memorize the formula or anything else like that. I do recommend it. But how are we feeling? Are there any questions or anything else that I can help with right here? Or are we feeling all right? And this is also part of the reason when I said that it's not really into or out of the page, because like part of it is, but then part of it's not. And so that's why I really don't want to think about this thing into or out of the page necessarily. Right? It's some strange oblique. Going into a little bit of both. Well, again, not both like that. In this case, we would have to write out our axes first. So if I wanted to do this x, y, and z, I'd say x goes that way, I could say y goes that way, and I could say z comes out of the page then. With those 3 things right there, I would be saying that this is probably a little bit more into the page. But it's also to the right and down. Right, so into the page, out of the page works very well when we're looking at 2 vectors on the screen for us, but that description doesn't go so well when we have things with multiple components. If there's nothing else right now, then I'm happy to say that's all I've got for the rest of the day. Thanks for being here. I always appreciate it and everything else. If there is anything that I can help with right now, though, I am still here waiting around until the next lecture starts. So do let me know. Otherwise, I'll see you guys next time.